Okay, let's continue our review for the Unit 1 lecture exam in astronomy by talking about light. So here is our lesson objectives for the exam. And then this is Chapter 5 out of your textbook. So these last three lessons that we're going to talk about, light, atoms, and telescopes, are all going to be found in Chapter 5 of your textbook. So you need to know the difference between a mechanical wave and an electromagnetic wave. You do not need to worry about the gravitational waves. So a mechanical wave requires something to actually carry the wave. So in the case of an earthquake wave, the waves are being transmitted because the rocks themselves are moving back and forth. In the case of a water wave, the water itself is moving up and down, and that is what's transmitting a water wave. In the case of sound waves, it's the air itself that is banging into each other that is transmitting the sound wave. So all of these are examples of mechanical waves. But then you have electromagnetic waves. So later we'll talk more in detail about what this is, but you've got on this side over here, we're going to say these are the radio waves, and then next to them are the infrared, which is heat, and then next to that is the visible part of the spectrum, and then next to that is the ultraviolet part of the spectrum, and then next to that is the X-ray part of the spectrum, and then next to that is the gamma ray. So all of these are different kinds of light. Now normally you don't call a radio wave a light wave, but it really is. So all of these are different forms of light. The one that we're most familiar with is going to be visible light. Now the big thing about electromagnetic waves is that they all travel at the speed of light, and they do not require anything in order to carry them. So that means that these things can go right through outer space. Mechanical waves have a difficult time going through outer space because there just isn't enough dust and stuff in order to transmit the wave. So you need to know some definitions for the exam. So the first one is going to be the amplitude, which is going to be the height of a wave. So on the exam, what I could do is I could give you a picture of a wave. I could give you a ruler and ask you to measure its amplitude. Now remember, it is not the distance from the peak to the peak. It's going to be the distance from the peak to halfway. So that's defined to be the amplitude of a wave. And for light waves, the amplitude is related to the brightness. So if this is a particular wave that has a certain brightness, then a wave that would be like this would be dimmer. Okay, it doesn't have as much of an amplitude to it. Okay, now I'm not going to ask you any questions about sound waves, but what I'm doing here is I'm comparing the electromagnetic waves, which are on the left-hand side, to the mechanical waves, which are on the right-hand side. So you notice that things are very similar when you talk about mechanical waves. All right, the next thing is going to be frequency. Now, depending on the textbook that you read, frequency could be the letter F for frequency, or it could be this symbol here, which is called nu. So that's a Greek letter, N, and this is the way that I'm going to do it. So I'm going to say that frequency is given by this letter here, but depending on your textbook, they might use that letter up there to indicate frequency. You do need to know that the official metric unit for frequency is going to be called hertz, so Hz, and it's going to be how often a wave repeats itself. So it's going to be, it's defined to be the number of times that the wave goes up and down per second. So it's how quickly is the wave repeating itself. And for light, the frequency is related to the type of light that it is. So on this side over here, these have the smallest frequencies, and on this side over here, these have the largest frequencies. And then visible light is going to have a frequency that's higher than radio waves, but it's going to have a frequency that's lower than gamma rays. So it runs the entire spectrum as you go across. And you'll notice that I give you the frequencies for the different parts of the electromagnetic spectrum, but you don't need to know about that. Okay, so don't worry about any numbers. And then I also give you the frequencies that go with sound waves, but again, do not worry about that because I'm not interested in mechanical waves. I'm interested in light waves. Okay, and then here again is some typical frequencies. All right, then you have wavelength. So wavelength is the distance the wave travels before it repeats itself. So if you measure the distance from here over to here, that's going to be the wavelength. And it's got its own special letter. So this is the Greek letter L, and it's called lambda. And it's going to be measured in meters because it is a distance. You measure it with the ruler. And you can also do the same thing for sound waves, but again, let's not worry about it. Okay, I also wanted to point out to you that that is a picture or a representation of what a light wave is. So a light wave is a alternating electric and magnetic field. And we'll talk more about that in just a few moments. Okay, so we've talked about what wavelength is, and we've talked about frequency. So how do they go together? And so it has to do with the speed of the wave. So in the previous lesson, we talked about what speed was, or velocity, and that was the letter V. Now I know this is kind of confusing because this is the symbol that I used for speed. So that's a regular V. And then this one here kind of looks like a bird with wings. And so this one is the symbol for frequency. So don't get them mixed up. So speed of a wave is going to be equal to its wavelength multiplied by its frequency. So that's a very important formula. And that's important because it's going to tell us something about the wavelength of light as it goes across. We know that this thing here has the smallest frequencies, but the question is, what would be the wavelength for a radio wave? And what would be the wavelength for a gamma ray? Well, this is going to tell us. Now, for any mechanical wave, which we're not interested in, but for any mechanical wave, they have unique speeds depending on what they're going through. So an earthquake wave may travel at 100 miles per hour if it's going through limestone, but it might travel at 200 miles per hour if it travels through granite, for example, which is a different kind of rock. So mechanical waves, because they're carried by the material that they're traveling through, they travel at different speeds through different materials. Okay, but light waves are a different story. All light waves travel at the same speed. So a radio wave travels at the same speed as a gamma ray, as an X-ray, as visible light. They all travel at the speed of light. And the speed of light is 3 times 10 to the 8th meters per second. Just to give you an idea for what that means, you could go to the moon going at light speed, which is incidentally going at impulse power in Star Trek. You could get to the moon in about 1/4 of a second going at light speed. So at faster than what you can blink your eyes. Okay? So that gives you an idea for how fast the speed of light is. So this formula here, which works for any kind of a wave, we're going to modify it for light waves, which is the only thing that you need to worry about on the exam. So instead of the letter V, we're going to put the letter C for the speed of light. So this formula works for light waves. So notice, so this is something you should remember from algebra, that let's say that 4 is equal to 1 times 4, but it's also equal to 4 times 1. So that would mean that if one number gets larger, the other number has to get smaller in order to compensate. So here we've got small frequencies for radio waves. So that must mean that they have large wavelengths. And we could put that on here. Large wavelengths go with small frequencies. Then over here, you've got large frequencies, so they must go with small wavelengths. And then in between, like for visible, it's going to be a smaller wavelength than radio waves, but it's going to be a bigger wavelength than gamma rays. So just to give you an idea for how small wavelengths can be, the wavelength of a gamma ray is about the size of the nucleus of the atom. So it gives you some idea for how small that they can get. So here is a type of question that could be on the exam. So what is the wavelength of a 91.3 megahertz radio signal? So the first step whenever you solve a word problem that involves numbers is write down what you're given. So the 91.3 is a frequency because look at the units. It says 91.3 megahertz, and hertz is the unit for frequency. So we know that the frequency is 91.3 megahertz, but that's the wrong unit. Hertz is okay, but we need to get rid of that word mega. So the capital M stands for million, so that's 91.3 times 10 to the 6th, a million hertz. And then it says, what is the wavelength? And we know that the letter for wavelength is lambda. Okay, now we plug everything into our formula so that we know the speed of light is 3 times 10 to the 8th. We don't know what the wavelength is, but we do know that the frequency is the 91.3 times 10 to the 6th. And now it is just down to algebra and your calculator to solve the problem. And then that turns out to be 3.3. And then the official metric unit for wavelength is the meter, so we would say 3.3 meters. Okay, let's keep going here. And another property of waves is called the Doppler effect. And so the Doppler effect is when both the wavelength and the frequency of a wave changes as the source of the wave is approaching you or the source of the wave is moving away from you. Okay, so for example, a train, so that's on the right hand side, if a train is moving towards you and then it blows its whistle, what you hear with your ear is the frequency of that sound is going to change, and so is the wavelength. Okay, so let's first talk about the frequency. So if something is moving towards you, the frequency is going to go up. So it's going to go up in pitch. Okay, now what does that mean if you are talking about light? Okay, now here are the frequencies. So this is low frequencies, high frequency. So if the frequency goes up, then that means that it's going in this direction. Okay, now what does that mean? All right, so in terms of color, we're going to talk about red shift and blue shift. So visible light is Roy G. Biv. Okay, so you've got red. I'm going to put the red over here. So red, and then orange, and then yellow, and then green, and then blue, and then violet. So those are the colors of light. Now notice that I put the red next to the infrared, and then I put the violet next to the ultraviolet. So that's how you remember. So if the frequency goes up, it's going in this direction towards the blue end of the spectrum. So we're going to say it's blue shifted if it's light. So if the source of a wave is moving towards you, the light is going to become more bluish. Now it may not actually be the color blue, but its color is going to shift in this direction towards the blue end of the spectrum. Now if something is moving away from you, okay, then the frequency is going to go down. So that means it's on this side over here, the small frequencies. So if the color is shifting in this direction, it's shifting towards the red end of the spectrum, and then we say it's red shifted. If something's moving away from you, it will be red shifted. If it's moving towards you, it's going to be blue shifted. Okay, but also notice something else, because on the exam I may not word it that way. I might say if something is moving towards you, what happens to the wavelength? Okay, and you see that the wavelength is going to go down. It's the exact opposite. So if the frequency goes up, the wavelength goes down, and you can see that because as the frequency goes up, the wavelength goes down. Okay? So, I'm not going to ask you any questions about sound on the exam, but I do expect you to understand what happens to light, and especially understand this red shift, blue shift thing, because the colors of stars really do change if that star is moving towards you or if that star is moving away from you. Okay, and then interactions with matter. So you can skip the stuff that is in the right-hand column because all of that is mechanical waves. But you should know what the word absorption of light means. So that means that as light tries to go through dust or through water, some of the energy is being absorbed. And so the brightness is going to start to dim as that light is passing through it. Then reflection is going to be when a wave bounces off of a material, like a mirror. So a wave comes in, and then when it bounces off of, that's the definition of reflection. Then you have refraction, which is going to be when a wave comes in and it changes direction when it goes through a material. So maybe this is water down here and this is air up here. So you can see that the direction changed when it went into this substance. So that is going to be refraction. And then diffraction is going to be the bending of a wave when it goes around something. So in this case here, that's a picture of a razor blade. And then if you take that picture and you blow it up, what you're going to see is it's kind of fuzzy around the edges of the razor blade, and also it's fuzzy inside of that razor blade. And that's because the light, as it is going around those edges, is being bent, and it's interfering with each other to make that fuzziness. All right, let's take a break, and when we come back, we will talk about what electromagnetic waves are.